Hello, and welcome to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. My name is Anthony Opapari. I will be the instructor of this course this semester. I'm very excited that you found our first lecture in this virtual format. So to get started, I'll just minimize myself so we can all see the slide material. There we go. And so welcome. So like I was saying, so this is the first lecture of this semester, and so this will serve sort of as a welcome and an orientation or initialization to the course and the topics that we'll be covering this semester. The agenda for this first lecture, we'll start with an introduction, introduction of myself and also my fellow course staff, followed by what is probably like the majority of the lecture. Essentially motivating this topic of robot operating systems and the crucial role that they play within the development of autonomous robots. Following that, then, we'll spend a bit of time going over course administrative details. So this will be policies around grading, how the projects will be distributed, what the schedule of topics is, things of that nature. And then finally, we'll spend whatever time is left then talking about some action items that you can take on your end to make sure that you're well prepared for the projects that we're going to start working on in these coming weeks. So with that, let me introduce the course staff. So as I was saying, my name is Anthony Opapari. So I'll be the primary instructor this semester. If you have any questions on enrollment or course administration that are urgent and you'd really like answered, feel free to email me. So my unique name is T Opapari there on the slide. So if you email, topapari@umich.edu, I'll get back to you as quickly as I can. In addition to that, I'll also have office hours this week and in the coming weeks on Wednesdays and Fridays. So I'll go into more details on how those are going to be sort of scheduled and run in the lecture here. But certainly, if you have pressing questions, do reach out to me so that we can, get any issues squared away. So in addition to myself, we have two outstanding IAs who will be working with us. So we have Tommy Cohn and Anna Warner, both of whom have taken the course in past semesters. And I'll let them introduce themselves at Wednesday's first interactive session so that we all can meet them. And then finally, we also have, as our faculty advisor, Professor Chad Jenkins, who has taught the course in the past and is also my personal academic advisor. So all four of us, would like to welcome you to the course this semester. We're really excited to be working with you, and we're really excited about this topic of autonomous robots. So just as a little bit more background about myself, so we're familiar. So I'm actually an Ann Arbor native. I'm from Ann Arbor. I did both my undergraduate degree and my master's degree in computer science from Michigan. So I took this course when I was an undergraduate student, and I taught it as a graduate student instructor during my master's degree. And currently I'm a PhD student. So I'm one of Professor Jenkins's students with research interests within robotics. So the projects that I work on generally are within what's called probabilistic robotics. So we try and study how we can make algorithms and techniques that will enable robots to understand their environment and their uncertainty about their environment based on their sensor input. And so one of the reasons that I'm really excited to be working with you this semester on this course is that I really do see robotics as the frontier of where computing can be applied within the physical world. So in the past decades, we've seen many successful cases of how computing in data centers and then in desktop computing and more recently mobile computing have solved many of our challenges. But so far, we're still sort of, I think, at really the forefront of how we can deploy computing in physical world situations with physical actuation, physical motors, and controllers. And so I'm really excited about this course in particular because this topic of robot operating systems is really what powers and enables robots to be successful. And so, with that, let's talk about this course. So the topic is robot operating systems. And one of the questions that I think most roboticists tend to ask themselves, I know I certainly do, is, where is my own personal robot, right? Because we see many really exciting applications of robots in pop culture and sort of in R&D, sort of like within, and in some cases within manufacturing. So, for example, on campus, I'm sure you're seeing the autonomous vehicles driving all around, still in that R&D stage. In the lower row, there's the Baxter robot within sort of a manufacturing setting. More recently, there's been quadcopters have been very common. But in terms of personal robots that we would use sort of within our homes or within our school environments, we haven't seen those as common yet. So in particular, I think what we're talking about when we talk about personal robots is mobile manipulation robots. So shown here, for example, is a fetch robot on the left and a PR2 robot on the right. These are robots that can drive around their environment. And then in addition, they have arms that are physically actuated, so they can interact with objects and other components of their environment to actually move them or manipulate them. And so these are the robots that I certainly find personally exciting when I try and think about what would be useful in my life to solve tasks for me or to perform actions on my behalf. But like I said, they're not quite common yet. And so one question you might ask is, well, how much do these robots cost? Is that a factor in their prevalence? And so these particular robots actually are very expensive. So this probably is one of the reasons why they're not so common yet. So the PR2, for example, which came out in 2009, was roughly $400,000 per individual unit. The Fetch, which came out 6 years later, dropped pretty substantially down to roughly $100,000 per individual unit. And so there's this trend of costs going down, which is good, right? Because that does increase the availability of these systems. As one anecdote, one story that Professor Jenkins likes to tell is that when he was a graduate student back sort of in the early aughts, the NASA Robonaut that he did some of his graduate studies on cost all the way up to $1.5 million. So there certainly has been this trend of decreased cost for robotic systems, which is really exciting, because what we're starting to see now is like the robots that that we would be working with in terms of like in industry or in our careers are going to be more affordable, and that means they're going to be more prevalent. So we're starting to see robots now on the order of tens of thousands within this mobile manipulation category. And so that's really exciting for us roboticists, because it means that there's sort of an increasing number of sort of interesting problems that we could actually solve with these systems. And so it's not just the cost, though, right? So the other big factor that sort of limits or enables these robots to be successful is what capability they actually have. So the earlier systems were typically limited to what's called teleoperation, which you can think about as being like remote control. So, for example, in the NASA Robonaut case, this was teleoperated by a human, shown here in this clip with sensors attached to them, where as the human moves its arms, those actions are sort of directly replicated on the robot. So these early teleoperation systems had very little, if any, level of autonomy, right? They were really just replaying, potentially in real time or close to real time, the commands and the actual behavior of some human kind of guide, or like some human oracle. And so this is good as a sort of a first step, and it's certainly useful for solving some problems where you can't afford to have a human specify very precise commands. But this is also a limitation, because many problems that we would be interested in solving with mobile manipulation robots can't afford to have a human looking over the robot's shoulder at every moment. So the trend that sort of happened in the past decade has been a move towards sort of higher levels of autonomy. And so what that looks like is, in particular, pick and place actions is what the field has really been working on. So here's an example from our lab where the robot is autonomously moving within its environment and then taking action on objects in order to rearrange them. So here, no longer do we have this human oracle specifying the commands. The robot actually is able to do this, on its own. And so increasingly, this is where the field has been moving. And now the sort of state of the art is towards what you might consider to be sort of higher level cases of taskable autonomy. So instead of saying like specific actions of like pick and place, put this object in this location, we're moving towards perform this task for me, which would be a series of actions aimed towards some goal. And so this is the trend that we've been seeing. And so as these costs have come down, so has the level of autonomy gone up. But if we look at these increasing levels of autonomy from the computational perspective, one observation we can make is that they can be thought of in terms of increasing levels of abstraction. So at the lowest level, we have our hardware platform of the actual robot, which using some very low-level signals could perform teleoperation. And then building on top of those low-level signals, you could perform pick-and-place actions. And to be a little bit broader, we should substitute dexterous manipulation for pick-and-place. So, just to say it's the set of robots that could perform sort of single actions, right? So like the NASA JSC robot, for example, could perform like actions with a set of tools, or the TU Munich robot on the right could perform single cooking actions. So if we make this substitution, you've got dexterous manipulation, and then at the highest level would be like a fully autonomous taskable robot, where a user could specify some goal. The robot could perform a series of these dexterous manipulation tasks to achieve it. And so using this framework of hierarchical levels of abstraction, we can recognize that it's a fairly similar setup to the type of problems that have been dealt with on deploying computational platforms, right? So desktop computers, mobile computers, they have to deal with levels of abstraction all the time. And typically what we're talking about when we talk about levels of abstraction within computing devices is the role of an operating system, right? And so an operating system, it's a specific piece of software that exists on a computing device that's responsible for interfacing between low-level hardware and higher-level applications. And so if we wanted to say it another way, we could say an operating system is what's responsible for kind of hiding the gory details of the hardware from the actual applications that sit on top of the operating system and interact with it, right? And so in the context of robots, this level of hierarchy is very similar, right? So if we want to sort of transplant each of these categories, just like in computing, a robot has a set of users. Those users want to run applications, which are the taskable autonomy. The low-level operating system of the computing device actually interfaces with the robotic hardware, but then we're left with this category that's kind of not fully defined, right? Which is dexterous manipulation. So what system would be responsible for performing those single kind of actions on the robot that would be needed for a successful robot application to interface with the low-level hardware? And so this is where robot operating systems sit. So we view in this course a robot operating system as a specific program that runs in between the computing operating system and the higher level robot applications. So this robot operating system would be responsible for hiding those gory details of the actual robotic device from the higher level application so that it can be sort of more efficient and much easier to actually develop. So again, at the lowest level, we have the robot hardware itself. Sitting on top of that, then, we have a computing operating system. So this would be an operating system that, like the ones that we're all familiar with. So this would be Linux, it could be Apple, Mac OS, right? Windows OS, Android OS, so forth. On top of that, then, sits our robot operating system. So typically, you'll see this would be something like LCM, or more commonly ROS for like robot operating system, although there are others as shown here. And so on top of the robot operating system is then how the users actually can perform applications, right? So the user would interact with a robot app, if you will, to perform some tasks that's directed by the user, and that robot application then would interface with the robot operating system. And so the question then is, what is this notion of a robot application, right? So when we say do this task for me, what does that really look like? So what we're really talking about is, or one way to think about what we're talking about here is this question of, can we make our world programmable from the standpoint of a robot? And so one framework that we could look at this at is from the standpoint of an app store. And could we make like a robot app store? So there's been a lot of interest in this topic actually in the past couple of decades. So there's been interest certainly commercially, but also from some of the early research in robotics. So in particular, this map it here was from Willow Garage roughly a decade ago, where they sort of envisioned this future of robots where a user could purchase a specific functionality for their robot, and then they could rely on that functionality without having to worry about the details of which specific robot hardware was running or which specific computer operating system was running. Right, it should be able to work and interface with them, right, regardless of the nitty-gritty details. And so this would be really desirable for a user. And so more recently, we've actually seen some trends that we're really moving towards this notion. So, for example, within Mac OS, they've been increasing the number of sensors on the mobile devices, and in particular by adding like a LiDAR scanner. So you actually see now applications in the Mac App Store for these devices that are really quite similar to what were envisioned for a robot application store, where you actually can ignore the user can ignore the details of the actual LiDAR scanner, but can use these applications seamlessly across different models and so forth. And so then the question becomes, well, could something like this exist in the future for a mobile manipulator like the Fetch? And that's really, I think, the goal of us who work in this field, is to try and build these robot operating systems and these robot applications that would enable users to seamlessly deploy their robots without having to worry about these very low-level details. Right. So in the future, we might imagine a mobile manipulator that you could afford being operated within some complex environment, as simple as sort of using any robot to perform a specified task in an arbitrarily complex human environment. That's, I think, the goal of our field, and that's really an exciting set of challenges there for us engineers. So, to look more broadly at how industry is looking to apply some of these ideas, there's a number of really compelling use cases for robots. So I've highlighted here on these next set of slides some that I think are very compelling, but there's really no shortage of where in the world robots can be applied. So for one here, there's these what's called like the 3Ds. So these are tasks that are like very challenging for humans or dangerous or too kind of like laborious and dull for humans, right? So this would be like infrastructure inspection, right? Nuclear cleanup or disaster response. Those kind of environments are really great for robots, right? They don't have to worry about the kind of innate human limitations. So in addition to that, then another really, I think, compelling case is social robotics. So how robots could be used within, for example, elder care or interacting with children in education or rehabilitation, to provide care and assistance to those who really need it. Similar to that is medical robotics. So this is one that where there's been a tremendous amount of research and a tremendous amount of investment, where robots are very successful in aiding surgeons and aiding other medical experts for very skilled operations. But this is just a few examples. There's really many others. So agricultural robotics, manufacturing robotics, security. There's one of the exciting, I think, parts about being in robotics is that we get to interface with computation, but there's also really no shortage of ways that we can apply these technologies. Having said that, there are ethical questions that come up, and so one thing that I would recommend you maybe think about as we go through this course is, where do you think robotics should be applied or maybe shouldn't be applied? It's one of the questions that I think the field itself is still, kind of grappling with. And so it's important that, I think as students that we do consider some of these questions. All right, so given all of those application, domains, this now is sort of our framework that we've set up for how a robot can be implemented, starting from the lowest level hardware, building all the way up to the highest level user specifications, and in between. And so the focus of this course is just on that middle component, right? The robot operating system. So we're not going to be using a sort of pre-implemented operating system like ROS. Instead, the goal of the projects in this course are going to be for you to build your own robot operating system, right? And so we're here to help, kind of guide that process. But really, hopefully, the outcome of this course is that you'll have the skills and the tools and the knowledge you need to build something that is comparable to a ROS. And so if we look within that, what's required to build your own robot operating system and what types of sort of mid-level actions and tools you would want for your robot operating system to have, there's a whole set that we could consider, right? So these are the tasks that would interface both with the low-level robot hardware and also the higher-level robot applications, right? So this is sort of middleware architecture. So some of the particular tools that you might want to implement would be something like localization and mapping, so that the robot could understand where it is within its environment. Path planning, so that your robot could plan trajectories and paths to execute actions, all the way up to higher level forms of planning like decision making systems or task planning, and then also topics like forward kinematics and inverse kinematics, so that the robot knows precisely where each of its joints is within the space, or in the case of inverse kinematics, how the robot should be configured to solve a particular desired state. So putting all of these tools together is what the robot operating system would be responsible for. And so, of course, we can't cover everything within one course, but what we try and do is cover, sort of at breadth, a number of these important tools. So highlighted in red here are the specific modules within a robot operating system that we're going to focus on within the projects of the course. And so within this framework, then there's one question that you might be asking, which is, will you be able, if we're dealing with robot operating systems and software, will you be able to work with the actual physical robot? So our goal in this course is for you to have the chance to work with a real robot at least one time during this course. And so we can do this using networking, where the robot operating system that you'll build can actually be interfaced with one of our physical robots, and then you'll be able to interact with it there. That's our goal. And so that then brings us to this course and some of the details of the course administration. So looking at our agenda, we'll go over the course administration, and then the final thing we'll talk about is a few action items that you should take on your end. So to start with, probably the most important resource for getting started in this course is our homepage, our website. So if you go into your web browser and you type in AutoRob.org, you'll be brought to a page that will look, it should look just like this, where you see the title of our course, and then you'll have a set of very useful information and links that will be used throughout the course. And so the first thing then that we should talk about in terms of course administration is probably what's on your mind is whether we're doing remote or in person. So we're doing a hybrid format based on the continuing situation with COVID. And so, but the important thing to know if you are remote and you can't travel back to campus is that AutoRob this semester can be done remotely. So we're going to support students that are fully remote, and we're also going to support students that are in person and a hybrid. And so to do this, our plan is to use a flipped classroom format where lectures will be recorded and posted online. So if you're seeing this, you're viewing a lecture that was recorded and posted online. And so these will be linked on the AutoRob homepage. So if you go to AutoRob.org and then you scroll down to the schedule, there will be, basically one entry for each of our scheduled course meetings. And for each entry, there should be a recorded lecture. And so those recorded lectures will be posted, in advance of the scheduled times. And then during the scheduled times, which are Mondays and Wednesdays from 1:30 to 3 p.m. Eastern Standard Time, we'll do an interactive session, which will be covering basically any general questions or issues that come up. So this could be, it might take the form of sort of office hours, like sort of sessions where we can work collaboratively on the projects. And then starting January 24th, we'll do weekly quizzes, which will just be brief, mostly focusing on project material. They're meant to be short, like 15 to 20 minute is sort of what we're aiming for, kind of quizzes. And so these interactive and so the quizzes can be done remotely. So we'll talk more about that once we get closer to those. And these sessions will also be linked on Zoom, so you can join live, or you can watch the recorded sessions if you prefer. And then, in addition to those interactive sessions, which occurs during the lecture time, right, Monday and Wednesday, 1:30 to 3 p.m. So in addition, we have then the lab sections on Fridays, which are scheduled for 2:30 to 3:30 Eastern Standard Time. So these will be done in person as well. The exact location is on the website. I think it's 1500 EECS is I think the room that we have. So these lab sections will also be recorded and also be available through that Zoom link, where the purpose of these will be to walk through the projects. So we'll go through project setup, or basically just walking through the code and what's required for each of the features that you'll be implementing. And then finally, another component of the flipped classroom which we're going to be supporting this semester is what we're calling interactive study pods. So we're going to essentially assign randomly like groups of like on the order of 5 students into these pods, with the intention being that you can work kind of collaboratively with each other on some of the project material. So you're not doing like paired programming or anything like that, but just the goal is to kind of give you like a smaller set of students that you can interact with throughout the class to try and encourage some collaboration in this hybrid format, because it is more challenging to interact with students when many students are fully remote or partially remote. So we want to try and encourage teamwork and collaboration in this way. So there will be more details on these study pods in the first lab section. So this coming Friday we'll go into more detail on those. And so to make this flipped classroom format successful, the first thing that we ask of you all is that you could fill out what we're calling the student workflow survey. So here's the link. So if you're looking at the PDF to go along with this lecture, this link is a hyperlink, so you can click on it directly. But we essentially just have a short set of questions that are really just intended to help us structure the course so that it's as useful as possible for you. So essentially, like what times you're most available, your GitHub account, we'll need that so that we can link your project code to the grader. What else is on here? I think the questions about like how you prefer to work on projects, just things that can help us organize the course so that it best suits your needs. And so the other place where you can find the link to this is if you go to the webpage and you just scroll down just a little bit, you will see this link here at this red arrow is pointing to. So if you follow that, it should take you to the survey. And we ask that you fill that out kind of as soon as possible so that we can incorporate that feedback into our scheduling for office hours and just how we kind of move forward with these initial weeks. So a couple other important resources on the website that I specifically want to mention. So if you scroll down just a little bit past this initial course format section, you'll see this course meetings section. So this is useful because it has links to the Zoom IDs, which we'll use for the interactive sessions and the laboratory sections. So once we have, so this will just be useful for you to refer to, I think for having this link. And once we start having these sessions, we'll store the recorded Zoom files in the course schedule. So if you scroll down below, or if you click the schedule link at upper left corner of the page, you'll be brought down to this subsection. So this is currently it's tentative, right? Because we're just starting the semester. But what you'll see in this schedule is the topics that we're planning to cover in each lecture and each lab session by the scheduled date. And then in addition, the sort of suggested readings that go along with each lecture, which is in the sort of middle column. And then on the right-hand column is the due date for project and quizzes. So as we move through the semester, what we'll do is we'll upload the recorded lectures to go along with each lecture session. And then we'll also upload the once they've occurred, the actual interactive sessions and the lab sessions to the schedule. So as we work our way through the schedule, you'll see additional links to these various recordings be appended as we go along. And then additionally, as we go along, the actual lecture files and the lab session files that are linked, which are PDFs, will also be updated so that they reflect the content that we're seeing this semester. If you click on some of the links that exist there currently, we've left the lecture slides from fall 2020 up, so that if you want to sort of move ahead, you can do that, but we might change topics slightly this semester. Okay, so with those two kind of important resources covered, the next thing that I want to talk about is the high-level structure of the course in terms of what it is that we'll be working on. So as we talked about, in the sort of motivation for the topic, right, the high-level topic of this course is autonomous robot modeling and control, kind of within this robot operating system framework that we discussed. And so the objective, like I mentioned earlier, is that you'll gain the computational skills, right, the programming skills, the modeling skills, so that you could actually build a robot operating system that could model and control a mobile manipulation robot. And so this is a project-focused class, so there will be 7 projects throughout the semester, which are intended to be individual projects, but we do encourage some collaboration, which we'll talk more about, where we're going to build up this robot operating system starting from a single joint controller all the way up to an articulated robot with motion planning, collision detection, and some really exciting topics. And so this is meant to be a computing-friendly introduction to robots. So the projects will be built in JavaScript, and we'll have a number of tutorials along the way to make sure that everybody has the resources they need to be successful with that. Which is another reason why filling out that student workflow survey will help us engaging your background. So in terms of course textbooks, so the official textbooks for the course are this Robot Modeling and Control by Spong. And then in addition, you could also refer to the Robotics, Vision, and Control by Peter Cork. Those are the 2 main texts that will kind of most closely align with the material from the course. But there's a number of other texts that you could also refer to if you're looking for additional resources. So these are outlined on this slide, and then there's a few others as well on the course website if you're looking for more material. So these are recommended. They're not strictly required, right? So we're not going to be like quizzing you on the readings or anything like that. But these will be useful for referring to as you start to implement the projects, because they'll give you a set of notation to go along with some of the features that you'll be implementing. That's really meant to sort of supplement the material that's covered during lecture. And if you have any questions about the textbooks, feel free to ask, through email or through some of our discussion channels, which I'll be talking about in a moment. So like I said, it's a project-based course. So the projects will be implemented primarily in JavaScript with a little bit of HTML, using what we call the KineVal stencil, KineVal stands for Kinematic Evaluator. So it's a framework that's built specifically for this course. And so the projects then will be submitted and tracked through GitHub. So if you haven't used GitHub before, don't worry. The lab section this Friday is going to cover sort of introduction to GitHub. But essentially, GitHub is a tool for maintaining what's called version control of software. So it's used for maintaining, tracking, and basically updating software projects as you work on them. So the course staff will have admin access to your repositories. And so by filling out the workflow survey that I mentioned, that'll ensure that we have your GitHub account, so we know which students are enrolled in the course, and we can link our accounts to their GitHub repositories. So we'll go into more detail in that in the lab section and in a few slides ahead. But so in total there will be 7 projects. 6 of them will be programming based, and then the final project will be sort of a presentation so it's not a programming based project, but it's meant to be more of sort of like a written or oral presentation. And so the grading for the projects then is broken down into a set of features for each project, where basically we check whether the features have been implemented successfully based on a set of test cases, and then the points are earned if the features pass the test cases. And so to do this, we'll use what's called continuous integration grading, which I'll talk more about on the slide upcoming. But the goal of this is to give you as much feedback as you need to be successful. So within these projects, the Kinival stencil itself is used for this course. It's designed for this course, and so it's a 3D. It's built on top of a 3D rendering library called 3JS. So this uses a combination of JavaScript and WebGL to do 3-dimensional rendering, all within a browser. So it's very efficient, and it's very friendly for visualizing and for interacting with as a developer. So this will rely on what's called URDF robot descriptions. So URDF stands for Universal Robot Description Format. And so there will be a series of projects that are built on top of this Kinival stencil. And so the one warning, which we do have written here, is that the stencil was primarily developed by Professor Jenkins, and so elements of it are what he calls professor level coding. So don't worry, we'll work through the stencil together. But you can do some really powerful things with it. It really is I think it's very cool and useful tool. So here's an example of some of the robots which we'll be working with this semester. So you can see that we can render some simple like geometric robots, which is what we'll work on to start with. But then we can work all the way up to full textured robot configurations, which are shown in the bottom row. So like the Fetch we were talking about earlier and the Baxter robot, those will actually be used and compatible with this code stencil. So the 7 projects that we'll be working on, these are the topics that they will cover. So the first project, which will be due in roughly from this Wednesday, from our first lecture, it'll be due roughly 2.5 weeks. So it'll be due January 21st. So this is meant to be sort of orientation project. So it's going to be to implement an A-star search algorithm in a 2D world, and based on that, sort of following that, then we'll work on a pendulum controller using what's called PID control, leading then into a forward kinematics project where we can actually then build a robot configuration in 3D space. Following that, we can then use our forward kinematics to implement a sort of pre-programmed dance routine for our robots. We then get into sort of more of the advanced topics of inverse kinematics, motion planning, and then the final project, which is the oral project, which is a presentation you'll give, or sort of a recorded presentation, depending on the situation, the public health situation, on what you think the best use of robotics is. And so one thing I would recommend, since we're just starting out, keep in the back of your mind throughout the semester, some ideas that you can maybe think of for what, the best use of robotics is from your perspective. So if you see sort of interesting news articles or as you're working on the projects, you'll probably have some ideas about where you think robotics could be applied to benefit society. And so I'd encourage you to sort of think about that throughout the semester, so that you'll have, a sort of good set of ideas to work on once the time comes around to present those. All right, so just as a bit of a kind of preview for what these projects will ultimately look like. So like I mentioned, so the first project, this path planning project, will be done in a 2D world, but following that, from project 2 up through project 6, we'll be working in a 3D environment within JavaScript and HTML. So here's just a few snapshots of the pendulum in the lower left hand side, and then the actual robot models that we'll be working with on the right hand side for projects 3 through 6. So these projects, like we mentioned, will be based on this Kine-Val stencil. So once you get initialized with GitHub, which we'll talk about in lab coming up this week, and I'll talk a little bit more towards the end of this lecture, essentially you'll have a private repository with your own private copy of this stencil, which you'll work out of. So all the projects in this course will be built within this, within your own repository. And as you basically build feature upon feature, you'll be creating this robot operating system that we've been talking about. So each of the projects is meant to sort of build on top of each other, all within your own private repository. And so, as I mentioned earlier, you will have the chance to work with a real robot. So, for those of you that want to, we'll support this by using what's called ROS-Bridge. So it's a networking interface which lets us connect your Kine-Val stencil with an actual physical fetch mobile manipulator, and it'll let you. It actually will let you send commands to the fetch for actions. I don't know if we'll get quite that far, but certainly interpreting data from the fetch and visualizing it in your Kine-Val stencil will do. And we might get to sending command actions to the fetch. We'll see. So with that, so that's the high-level set of projects that we'll be implementing throughout this semester, which then leads us to the course policies. So in terms of grading, to be as transparent as possible, this is how the grading policy for EECS 367 and also Robotics 320 will work. So there will be, like I said, 7 projects total. Each project is worth a total of 12 points, and these points break down in terms of a number of features, which will be detailed on the course website for each project. In addition to the projects, then I mentioned there's 10 quizzes, which will be roughly once a week starting January 24th. And these quizzes are meant to be short, so they're 2 points each. And then there's 4 points for participation throughout the semester. So this would be like interacting with the course staff through Slack, interacting with your collaborative study pods, I think we called them. So 4 points total for that. And then in addition this semester, we're offering 4 points total of extra credit, which can be earned by implementing extension features on top of the required features for each project. So there's more details of these extra credit features given on the course website. As the projects get released, we can I'll talk more about what features could count for these optional extensions, but they're also detailed for each project spec. So based on this set of projects, quizzes, and participation, the grading then will break down into the scale given here. So if you get a total of 95 or more points, that will be some form of an A in the class. For a B, it'll be if you get above 83 points, and then a C above 73 points. So we're trying to be as transparent as possible. So there's not any final exam or midterm exam. It's really meant to be a project, focused class. So if you have any questions about the grading policy, don't hesitate to ask. We're happy to answer or clarify any questions as they come up. So in addition to this portion of the grading policy, the other portion, so we'll be using what we call this continuous integration grading. So this is meant to really be an experience similar to what you would experience on development sort of in industry, where continuous integration testing is used quite frequently. And so the other goal of this is to give you as much feedback as you need to be successful. So the way that this CI grader will work is essentially every day it will pull code from your repository. It'll run a set of tests for all the projects that we've seen up to that day. And then it'll return the test results to your repository so that you can see. And again, it's private to just you. Based on, along the way, the course staff will also review the grades that come out from the CI grader for correctness. So we'll also be familiar with your code base, where you stand with the projects, and able to give feedback. It's not just going to be this CI grader. So following on, so we do have sort of a late policy within this class. So any projects that are submitted after the deadline might not be graded, but if a late submission is allowed based on the course staff's basically allowing it, then it can receive at most the following partial credit. So the goal of this course is for you to finish projects on time, but if there are extenuating circumstances, then we do have the right to allow for late submissions, but really the goal should be for you to submit the projects by the deadline. So you can refer to this slide for some of the details on this, on the late policy. One thing I should mention, this final grading deadline that should be updated to April 18th. I will update that in the posted slides. But yeah, so feel free to ask any questions about this that come up. The details of this policy are detailed on the course website. But essentially the goal is for you to submit projects on time, but if there are extenuating circumstances, we will allow late submissions for partial credit. In addition, we also have a regrading policy. So each project feature that's assigned could be graded within one of 3 states. So either it's sufficiently completed, which is it passes the continuous integration testing, it's due, so if it doesn't pass all the tests, or if it hasn't been completed, then it would be in the due state, or pending if there's if it hasn't been assigned yet. So for all the projects that haven't been assigned, those features would be returned as pending. So if you've made a submission but you haven't passed all of the tests, and so that feature would be marked due for insufficiently complete. If the project deadline for that passes, you can request a regrade for partial credit, so 80% credit if your fix is pushed within 2 weeks of the returned grade, or 60% credit if it's pushed any time before the final grading deadline of April 18th. So this is the regrading policy, and that kind of covers the grading for this class. And again, all of those details are described on the course website as well. All right, so next, in terms of policy, so for collaboration, so all work that's submitted has to be your own. So we will be following what we call the Michigan Honor License, which I'll talk about on the next slide. We're also operating, within the College of Engineering, so the Engineering Honor Code applies to all the work that's done in this course. So you cannot communicate code directly between yourself and other students, right? So you can't copy code or send code to your colleagues in the course. And any external sources that are used should be cited. And in addition, your repositories have to remain in what's called private mode for compliance with the honor code. But having said that, we do still encourage a collaborative environment. So discussing ideas generally, apart from specific code implementations, we encourage. That's a healthy academic environment. So we are, discussion is really important for generating ideas and and improving. So we do encourage that. And so to facilitate that, we have this Michigan Honor License. So it's sort of a mixture of BSD license with the Michigan Engineering Honor Code and like Creative Commons license. So when you submit your projects, you'll have to assert that you're complying, that your code complies to this Michigan Honor License. And so the way you'll do that is within your repository, there will be a license file. So if you append your name to the license file, we take that as a form of a digital signature that you've been following this license. And so any code that's submitted will have to assert this license for it to be graded. So we won't grade any code that has been submitted that doesn't assert the license. So it is important that you do append your name to that license file. So I'll talk more about the details of how to do that in the upcoming lab. Okay, so with that, another important detail is the discussion and communication forums that we will use this semester. So in particular, we'll be using an AutoRob Slack workspace through the University of Michigan Slack. So if you're enrolled in the class, you should be automatically added to this Slack workspace. So if you go to this address here, this um-wn22-autorob.slack.com, you should have access to our Slack workspace where we encourage formal course discussions. You can talk about the projects with your peers. This is a public, if you're not familiar with Slack, it's sort of there's public channels where everyone in the course has access to, and then you can also private message. So you can private message the course staff if you'd like. If you have questions that are sort of specific to your project work or to your questions specific to yourself, feel free to ask us. And you can also collaborate amongst, with your peers, through individual channels. So in addition to that, for communication, so with the course staff, each member of the course staff will have weekly office hours. And so we'll try, our goal, I think, is to support a hybrid format. We're going to base that on, public health considerations. So for the first week, it'll be, we'll do all virtual office hours. And so our, the details of that, I'll talk about, I think, in an upcoming slide, but also on the course website, we have all the links to like our Zooms and our office hour queue on the website. And so then here's my email again. If you have any questions or concerns, if you don't have access to Slack, for example, feel free to email me. I'm happy to respond through email as well. So for those of you maybe who haven't used Slack before, so once you log on, this is what you should see. Certainly the general channel, at least here. So Slack is basically a messaging kind of forum, like I mentioned. So we'll use this as the primary means of communication in terms of updating asynchronously. So, but again, if you have questions, you can post to the specific project channels, which are shown here, or if you have general questions, administrative questions, you can post them to the general channel, and then also we have a random channel. So if you come across interesting news articles relating to robotics, feel free to post those to random. They'll be if they're of interest, to your peers. It's always fun, I think, to discuss those kind of tangential topics. And so Slack is a good way of doing that asynchronously. Yes. So the other thing then, so in terms of office hours, so in the past when I've been teaching this class, they do get very, very busy. And so one thing we want to do this semester to try and make sure that everybody has sort of a fair access to the course staff as a resource, we're going to be using the EECS office hours queue. So this is the web address to the queue. It's also posted on the course website. And so if you go to this web address, it's hosted through eeks.umich.edu. You can see EECS 367 as one of the courses. So during our scheduled office hours, which, so again, like I have office hours Mondays and Wednesdays and Fridays, and our IAs will have weekly office hours as well. So during our scheduled office hours, this queue will be open, and you'll be able to sign up for a time slot or multiple time slots within the within the office hour session, and we will then answer any questions, or we can discuss the project or lecture material, or robotics more generally, depending on your needs and what would be useful. So this will be an important resource. I think especially as projects come around, that tends to be when office hours get used substantially. Okay, so that covers the course administration. So the final sort of topic for today's lecture are a set of action items that really we as the course staff need from you. So there's three main ones. There's the student workflow survey, there's making sure you have access to our Slack channel, and then also joining our GitHub classroom. So we'll walk through each of these. So the first thing is to make sure you complete that student workflow survey, as quickly as possible. So here once again is the link to that. It's also like I mentioned earlier in the talk, it's also available on our AutoRob.org homepage. But again, if you can fill that out as quickly as possible, we'd really appreciate it. It's really meant for us to be able to help you. It's just information that helps us kind of organize the course. So once you've completed that, the second thing you should do is make sure that you can access the AutoRob Slack workspace. So there's a link to the Slack workspace on our homepage and also embedded in this PDF slide. So if you click on that link, it should take you to the Slack workspace. You should have to log in with your UM credentials, so it should be linked to your unique name. But let me know by email or at my office hours if you have any issues with Slack or getting access to Slack, and we can resolve those. The third thing then that you should do is to start to work on installing Git and setting up your local environment. So to do this, the lab section this week is going to be dedicated to setting up Git. If you haven't used it before, that would be a very useful resource. But if you're looking to get started even before Friday, there's a section on the website that's towards the bottom, but there's also a hyperlink at the upper left-hand side titled Git. So if you click that, we have a section on the website dedicated to how to sort of get started with Git. Once you have a GitHub account, we ask that you join the AutoRob GitHub classroom. So if you click on this link here, we also have, like I said, we also have this embedded on the course website. But if you click on this link, it's an invitation to join our specific GitHub classroom, which we'll be using this semester. So it'll take you first to this page that allows you to join the classroom. So if you arrive at this page, we ask then that you click the skip to the next step link, which is shown in the dashed red box. Once you do that, it should take you to a page like this where it'll create automatically for you a clone of the Kinival stencil. So this will be linked to your specific GitHub account. And so it should be titled Kinival-stencil-your username. So where we have here like -student, it should be unique to -your username. And so once that process has occurred, you'll then be able to access your own private Knievel stencil repository, which should look something just like this. So once you've done this, you'll be set up to start working on the project. So at this point, you should then, once you have Git installed locally, you have your GitHub account, and you have your Knievel stencil, you should then be able to clone your repository to your local environment and begin working on the projects. We'll spend more time going through this on Friday, each step in more detail. But at a high level, those are kind of the three main steps: is install Git locally, access our GitHub classroom, and then which will automatically create your private repository. So that brings us then to the wrap up. That's really all the topics for our first lecture. I know there was a lot of content. So just as a summary, or sort of like what we're going to be doing in the next few kind of course meetings. So the I'll see you on Wednesday for our first interactive session, where we'll sort of introduce ourselves, and we'll probably begin talking about Project 1 and some of the details of Git. But this week's lab on Friday is going to be dedicated to a walkthrough of Git and a walkthrough of the Kinival stencil in more detail, so that you'll be all set to start working on the course projects. And then next week's lectures are when we're really going to start diving into the robotics material. So we'll start on Monday with a lecture on path planning, and then Wednesday's lecture will be dedicated to JavaScript and also the Kinival stencil. So just one final reminder is that the assignment 1 has been officially released. So the specification is up on the course website under the assignments section, and it will be due January 21st at midnight. So you'll have from the first lecture time of Wednesday, you'll have about 2.5 weeks for this first assignment. But with that covers our first lecture. And once again, I'm really excited to be working with you this semester, and I will see you on Wednesday or on Friday. Thank you.